Good day everyone, welcome back to my channel. And today we are on lecture 5 of this series of what machine. So in today's class we will be discussing three-phase balance system. Three-phase what balance circuit is what we'll be discussing in today's class. Now, a three-phase circuit is an electrical system made up of what three alternative voltages or current. Now, it means in a three-phase system, it has what three-phase voltages, three-phase AC voltages, or three-phase what AC current. And now these three-phase voltages and three-phase current, they have the same frequency and the same magnitude. However, they are displaced from one another by what 120 degrees centigrade degrees, right? 120 degree electrical degrees. Yes, when you sum the three up, it will give you what around 360, right? Now, three-phase systems are widely used in power generation, transmission, and even distribution and industrial machines because they are more efficient than single-phase system. So in power engineering, most large generators produce three-phase voltages. Transmission lines carry three-phase power, and most industrial motors operate on three-phase supply. Now, normally, what this is talking about, when you see yes, in a good example is what a generating station. You see that generating station, the generator, the alternator they use there is three phase, which means it's three wire system, RYB that's coming out from what the generator, and the three system, the three phase, definitely they have what the same frequency and what the same magnitude, definitely if the system is balanced. But however, if the system is not balanced, then it means some voltage may be higher than what the other, but normally it's supposed to have what three phase voltage or three phase current that are what all the same and also what the same frequency. Now, a three-phase system is said to be balanced when the key things happen. One, the voltages are the same in the three phases, right? If they have equal voltage magnitude, then we say what the system is balanced. Also, three-phase voltage have the same frequency, right? Once they have the same frequency, then we say the system is balanced. Then also the phase voltages are displaced from one another by exactly 120 degrees. Then the three loads have equal impedance, which is the Z now is what are equal. Then for mathematical what representation of what the three-phase system, we have what this is the order, which is what red, yellow, and blue called what RYB. So my red phase is what my red phase is V phase less than 0 degrees, while my Y phase is V phase less than minus 120 degree, and my blue phase is what V phase less than what 120 degrees, which means they are what 120 degrees apart. Normally, my VRO is what the voltage at the red phase, the voltage at the yellow phase, and the voltage at the blue phase. Now, it's better we know the advantages of three-phase system. Yes, advantages of what three-phase system to make what to give us a better understanding of what three-phase is talking about. One of the advantages is that they transmit more power than single-phase systems using the same amount of conductor or material, conductor material. Now, when you are using what the same conductor material, definitely our three-phase system will carry what will transmit more power. Yes, it will transmit more power because it's three. While single just be transmitting single power, but for the three phase it will be transmitting like three times of what a single phase is transmitting. Then two, three-phase motors, they are self-starting, and three, the power deliver a balanced three-phase system is almost constant. Yes, the power delivered in a balanced three-phase system is almost constant. Then the next is what they are more economical for long distance what power transmission. That is why we tend to use what just three phase for what power transmission. And also, three-phase machines are smaller, lighter, and more efficient than single-phase machines of the same rating. Now, generation for three-phase voltage. Now, as you can see from this our diagram, a three-phase voltage generator when three coils are placed 120 degrees apart. As you can see, we have R, Y, B. From here, you can see that the red is starting from 0, like this, right? The yellow is starting from negative minus negative 120, and the blue goes like this, right? Which is what positive, the blue is supposed to be positive 120. Definitely it will be like this. However, my blue face was supposed to move from this side, right? I think there's an error here. My blue face was supposed to move from this top, which will signify that is what is positive. Now, three-phase voltage do not reach their maximum value at the same time. Yes, as you can see, this one is at maximum, but this one is not reaching maximum yet. It may be at minimum. When this one is already at maximum, you see, this one is not what at maximum, which means the three voltage does not reach what their maximum value at the same time, because they are what displayed by what 120 degree apart. Now, the phase sequence is what RYB. RYB, that is what the phase sequence. So the phase sequence is the order in which the three-phase voltage reach their positive maximum value. So our red will go to its maximum value first before yellow, and yellow will get to the maximum value before what B, or what ROBY. So for a positive phase sequence, we have them in this form. So when red phase is at 0, yellow phase is at what minus 120, and blue phase is what at what 120 degree. The phase sequence is very important in three-phase motor because it determines the direction of what the rotation. Immediately, or once you what alternate, once you change the direction, then the direction of connection, then definitely is going to what reverse the direction of rotation of what the motor, if it's motor that you are connecting. Now, the basic terms, yeah, basic terms in three-phase circuit. Some of the terms that are used in three-phase circuit, they are what? We have the phase voltage, we have the line voltage, we have the phase current, and we have what? The line current. So for the phase voltage, it's denoted by D. The phase voltage is the voltage across one phase of a load, right, and is rated by this, while the line voltage is the voltage measured between two lines. Yes, when you are taking voltage between two cables, it's called what? The line voltage. But the phase voltage is the voltage across one phase, right? So phase current is the current flowing through one phase of the load, while the line current is the current flowing through each line conductor, which and is denoted by this for the line current and this for the phase current. So types of what three-phase connection. In three-phase connection, we mainly have what? Two major connections, right? Two major connections. We have the star connection, which is denoted by Y most of the time. So you still call it either you call it what? Y connection, or you call it what? Star connection. Then we have what? Delta connection, also known as what? This delta. Now, for the star connection, it means definitely for a system to be balanced, it means all the impedance should be equal. That is one, right? All the impedance should be equal to what? To our our Z phase for line connection. Now for star connection. So in a star connection, one end of each phase, you see, one end of each phase are what? Connected together, which will form what? The neutral point. right? So if this phase 1, phase 2, phase 3, one end of what the three phases are joined together, then here we have what our neutral point. And for a balanced system, the three impedance, the impedance this and this are supposed to be equal, and which is equal to what our Z phase. Now, voltage relationship in star connection. So don't forget, in star connection, our V line is root 3 of what is the V phase, right? The V line is root 3 of V phase, which means our V phase is what V line divided by root 3. Also, the line voltage leads the corresponding phase voltage by around what 30 degrees. One of the you have to note this is very important in what star connection. Our V line is what root 3 of the V phase. Now, what about the current? Now, in star connection, the line current equals the phase current. So it means my I line is the same as what my I phase. Now, the summary of what formulas in what star connection. My V line is root 3 of the V phase, while my phase voltage phase voltage is V phase equals what my V line divided by root 3. My line current is what is the same as what my phase current. So my phase current is what my I phase divided by what my V phase divided by what my Z phase. So I said my phase current is what my V phase, that is voltage at the phase, divided by what the impedance, the phase impedance. Now for data connected balanced load, in data connection, the three phase winding or loads are connected end to end to form what a closed loop, just like this. So they are connected end to end to form what a closed loop. So and don't forget, for a balanced delta load, all the impedance these are equal, and which are the same with what the Z phase. So the voltage relationship and current relationship in data connection. For data connection, the voltage, the V line and the V phase are the same, they are equal. However, for the current, my I line is root 3 of what the I phase, or the I phase is I line divided by what root 3. And the line current lags or leads the corresponding phase current by what 30 degree, just like what we saw in star connection. Now the relationship, my V line and my V phase are the same, which are this, and my I line is what root 3 of what my I phase, or my I phase is what V phase divided by what my impedance, phase of what impedance, or impedance per phase. Now the balanced three phase load. Now for a load is said to be balanced when the impedance in each phase is equal. Now if my what impedance at what the red phase is the same as the impedance at the yellow phase, and also the same as the impedance of the Z phase, sorry for that, then we see what the three what impedances are equal. Now each impedance has the same magnitude and phase angle. For example, we have our ZR, ZY, ZB to be what 10 less than what 30 degree ohms. Now it means our Z, our impedance at the red phase is this, our impedance at yellow phase is this, and same as what the impedance at what the blue phase. Now impedance of a phase, we said our impedance is the summation of what our resistance plus what our reactance. So this is same as what the magnitude of what our Z is what the root of what R square resistance square plus what my reactance square. Now if I'm looking for what my angle, the impedance angle is tan inverse reactance divided by what my resistance. So now let's discuss about power factor. We normally know the power factor to be what? The cosine of the angle between the voltage and the current. Now, which is what the power factor, we call it TF, is what? Cos theta, right? It's cos theta. So the theta here is the phase angle between the voltage and the current. Now, power factor ranges from what? 0 to 1. So it ranges from what is 0 to 1. When your theta is 0, then the cos theta or power factor will be 1. But when your theta is 90, then power factor will be 0. And normally, most of the power factor is in between 0 and 1. So whenever you have 1, then it means what? The power factor is unity. We call it what? Unity power factor. Yes. Now, power in balanced three-phase circuit. In a balanced three-phase circuit, the total power is the sum of the power in the individual phases, right? So if this is the phase, the power per phase, then I have what my V phase, my I phase cos theta. Don't forget this what the real power. Then it means my total power in the three phase is this multiplied by 3, right? And this can also be written as what this general formula. So for here, I'm using what my phase. This is my phase voltage, that and my phase current. But if I tend to use my line, it means I should be able to root 3 V line I line cos theta. Now, talking about the types of power in a circuit, we have what reactive power, we have what apparent power, and we have yes, we have reactive, we have repower, and what apparent power. Now, for the reactive power is given by this 3 V phase I phase sine theta, right? Which means my Q, my reactive power at the line is 3 VL IL sine theta. The reactive power is measured in volt ampere reactive. Volt ampere. So from what our power triangle, normally the power triangle is what the relationship between what our active power, reactive power, and what apparent power, which is what shown here. However, looking at this, our P was supposed to be here, and our S is here. It's what a typographical error from here. So what the square of what our apparent power is what the summation of the square of what the real power and what the reactive power, which will then give us what our power factor to be what the real power all over what apparent power, and our sin theta to be what the reactive power all over what apparent power, and tan theta to be what reactive power over what real power. Now our apparent power is root 3 of what our line voltage and line current. Now, the apparent power is measured in VA, our real power is measured in watt, and our reactive power is measured in what? Volt ampere reactive, or VAR, VAR. So neutral current in balanced three-phase system. We know that our neutral current in balanced three-phase system is normally what is 0. This is as a result of that the neutral current is the phasor sum of what the 3 watt current. And don't forget, since these 3 current are the same, once you sum them up, it will give us what it will give us a 0 degree. And don't forget, they are what 120 degree displaced apart. This means that no current flows through the neutral conductor in a perfectly balanced system. So the phasor diagram of what the balanced three-phase system, we have what our VR, then we have what our VB, which is positive 120, then we have what our VY, which is what negative 120. Now, comparative analysis between what the star connection and what the delta connection. So for our star connection, we can see that for the phase voltage is V phase, which is what V line divided by root 3. For the current, the phase current and the line current are the same, and the neutral point is available for star connection, and this is mainly suitable for what high voltage, low current, and they are mainly used for what transmission and what distribution system. While for the delta is noted by this, our V phase and what our V line, they are the same. However, our I phase is what our I line divided by root 3, and this type of connection does not have what a neutral point, and is suitable for what low voltage, high current, and is mainly used for motors and heavy what loads. Now solving balanced three-phase circuit. Now let's take some let's try to solve some question. However, before we solve that, let's give what is the steps that you are supposed to follow when solving for balanced three-phase circuit. Now, to solve the balanced three-phase circuit problem, we should follow the following step. Step one, identify the connection type. Is the connection type circuit is star connected or delta connected? So you have to know that in order to know how to calculate what your phase voltage and what your line voltage is. Then step two, find the phase voltage after you have identified that either it's delta or star. If you have identified that it is delta star connected, then this is your V phase. But if it's delta connected, then this is what your V phase with respect to what to the V line. Then the third step is what to find the phase current. Now, if you have identified that it is okay after getting your voltage, then you can use this formula to calculate for your phase current. And for the step four is to find the line current. For star connection, you already know the line current and the phase current are the same, but for delta, our line current is √3 of what the phase current. Then step five is to calculate the power. So we have our real power to be √3 V line I line cos theta, while reactive power is √3 V line I line sin theta, while our apparent power is √3 V line I line. So a balanced star connected load has a phase impedance of what 10 less than 30 degree ohms, and the load is connected to a three-phase supply or V line to what 415. So we are told to find the phase voltage, the phase current, line current, and total active power. And don't forget what kind of connection it is star connection, which means the system is what star connected. So to solve this, for a star connected system, our V phase is V line divided by √3. Now our V line was going to be 415, then divided by √3, we have what our V phase will be this, which is what approximately what 240 volt. Now if we to calculate for what our I phase, it means we have to use this formula. Our V phase divided by what our impedance phase. Our Z impedance was given to about 10 less than 30 degrees, and we have already calculated what our V phase. So we have this, which should definitely give us 23.96 less than what minus 30 degree amps. So it means our I phase is approximately what 24 amps. And don't forget this star connection, and it means our I line and what and our I phase are the same, right? They are the same. So if they are the same, then it means my I line is what 24 amps. Then for the power factor, right? For the power factor, our theta was going to be 30 even from what the impedance. That means we have what cos theta equals what 0.866. Total active power, which is what number 4, the active power, which is what the real power is P equals to √3 VL cos theta. So we have P equals to √3. Our VL was 415 and our IL is 23.96 multiplied by 0.866. So it means our real power is around 14.9 kilowatt. So to really solve this, you can decide to pause the video and solve it yourself. So we have another question here. We have another question. We are told the balanced delta connected load has a phase impedance of Z phase to be this 20 less than 60 degrees and connected to a three-phase supply of VL of around the 400 volts. So we are told to find what the phase voltage, phase current, line current, total active power. Now, this is what a delta connected system. Then it means my V phase and my V line are the same. So if my V line is 400, then it means my V phase should be 400 volts. Then to calculate the phase current, I will have we have our total active power to be P equals √3 VL. Okay, sorry, I think I'm in this part. So my I phase equals what V phase divided by what Z phase. My V phase is 400 less than 0 and my I phase is 20 less than what 60 degrees. That means my I phase should be 400 divided by 20, then 0 minus 60 will give me this. So my I phase is what 20 amps. and this is what delta connection. Then it means my I line should be what root 3 of what my I phase. Then multiply it with root 3 and we have what 34.64 amps. So now let's calculate what the power factor. Our theta is what 60 degree as it was given in the question. Then we have cos theta, which is cos 60 equals what 0.5. So total active power is my P equals root 3 VLIL cos theta. So I have my root 3, my VL is 400, my IL is 34.64, my cos theta is 0.5. So we have what my P to be what 12 kilowatts, right? Don't forget this is what data connected system. Then we have another question. To be a balanced three-phase load takes a line current of I line to be 30 amps from the three-phase supply of V line is 415. If the total power consumed is 18 kilowatt, find the power factor. Now we are given P, right? We are given P to be what 18 kilowatt. So solution the three-phase power equation is this: P equals root 3 VLIL cos theta. Don't forget, in this system we are not told whether it's what delta or star connected. Then it means those connections may not be useful, since we may not need them to solve what the question. That is why it was not given. Whenever we will need them, then definitely it will be given. So we have what our P equals to 3 VLIL cos theta. So our cos theta equals what? P divided by root 2. When I divide both sides by this, so we have this. So my cos theta is what? My P divided by this. So cos theta is what? 0.835. Right? Now we now assume if this load is what? Inductive load, then it means it will be what? 0.835 lagging. But if it's capacitive, then it means it should be what? Leading. So start to data transformation. There are times they give you your connections in data format, right? While there are times they give you in star format. So to find the equivalent or to convert it to the next connection format that you need, then these are what basically what's the formula. So data to star, we have what my impedance in star connection is what the delta connected impedance divided by 3. But for the star to delta, that means what my impedance in delta is 3 multiplied by my impedance in star connection. Why balanced three-phase circuits are easier to analyze? There are some reasons that solving a balanced system is far better. Even looking at the name, it's balanced. It means the system will be simple for you to solve. It will be easy for you to solve. So the balanced three-phase circuit are easier to analyze because all the three phases have the same behavior. They behave in the same manner. Then it means you solving one, you can use it to get others. Once you get one, then you assume that others are the same because the system is balanced. Therefore, instead of solving all the three phases separately, we can solve only one phase and use the result to determine the others. So this is called single phase equivalent analysis for a balanced system. Don't forget, when you sum the three voltages together, it will give you 0. And also when you sum the three currents together, it will give you 0. So single phase equivalent circuit. For single phase equivalent circuit, we have what our I phase will be what is Z phase divided by what the V phase divided by what our phase impedance. Once the current in one phase is known, then the current in other phases are equal in magnitude but displaced by what 120 degrees. Now, practical applications of what balanced three-phase circuit are: 1. Balanced three-phase circuits are used in three-phase induction motor, synchronous motor, industrial heating system, power transmission lines, distribution transformers, large pumps and compressors, welding machines, factories and workshops, and high power electrical installation. So the summary of this class is want to try to summarize all the equations that we have listed, all the basic equation. For star connection, our V line equals what? Our root 3 V phase. while our I line is the same as what our I phase in star connection. So our V phase is what V line divided by root 3. Then for delta connection, our V line is same as what our V phase, and our I line is root 3 of what our I phase. So our I phase equals what our I line divided by root 3. So some questions that you need to solve, try to solve them, and you can paste your answers on the comment section. The first question is that a balanced star connected load is supplied from a 3-phase 400-volt supply. Each phase has an impedance of 8 plus j6 ohm. Don't forget, this is what rectangular format. You can convert it into what polar format, before using it. So calculate the phase voltage, the phase current, line current, power factor, total power consumed. And this is question 2. For question 2, you can pause it to read the questions. Yeah, just pause it, take down the question, try to solve. This is okay. We have question 2 and 3. Then here we have question 4 and 5. Actually, those questions are very easy. Try to go through the video several times to have what a better and a comprehensive knowledge of the topic. And if you think there are some things you are lacking also, you can ask on our comment section, or you can refer to textbook for better understanding. So concluding note, a balanced three-phase circuit is one of the most important concepts in electrical engineering. Once the relationship between line and phase quantities is understood, analysis becomes simple. The most important point to remember is that for star connected, our V line is what root 3 V phase, while our I line and our I phase are the same. For delta connection, our V line and our V phase are the same. However, our I line and our I line is what root 3 of what the I phase. So for both star and delta balance system, our active power or real power is root 3 VLIL cos theta. This equation is one of the most widely used formulas in three-phase power system analysis. So thank you for listening, thank you for watching, and don't forget to share and also subscribe to our channel. Bye for now. Spark, scholar from idea to paper. Bye and have a nice day. See you in our next video.